My Barry Mary Science Lab, and welcome to the F equals MA exam 2020B question 6. This was the hardest one to understand for me so far. Let's say we have an equilateral triangle. And this equilateral triangle is not just any equilateral triangle, it's a table. A table with one vertex at each leg. So this is from a bird's eye view, obviously. And the legs are going into the smartboard. So what are we looking at here? Well, basically it says when we put a mass here, a point mass that has a mass m, then all three legs simultaneously break. So I'm just going to put a little arrow here. All three legs, let's put the mass back in. Do that a little later because I love procrastination. All three legs are gonna snap in half simultaneously. So, with that said, and the knowledge that all legs are identical. Oh yeah, and the knowledge that if you have any mass less than m and put it in the center, none of the legs will break, then what is the largest? No. If you have a second mass, this time 2/3 m, and you remove the mass of m from the table, what region can you put 2/3m in such that no legs break? This is a tricky boy, and it requires a lot of intuitive thinking. So first of all, let's have our three vertices, A, B, C. So now, if we can take any point in the triangle, whoop-de-doo, whoop-de-doo, and this is where our mass is going to be. What we can do is let's lower the thickness, we can consider an axis that is parallel to one of the sides and goes through the mass. And now you might ask, why parallel to any one of the sides? Well, because that makes it more convenient for us. And because if we had it say at any random thing, like here, for example, then the distance from here to this leg would be something that would take an eternity to find. So, now we can do it this way, or we can do it parallel to any one of the three sides. So we could do it this way, or we could do it this way. But for our sake, we're not going to go through all three cases and just go through one. Because of rotational symmetry, all three give the same results. Not symmetry, symmetry. So, this is 2/3 m. Now, after all that yada yada blada blada, let's define this. Oh my god, it's painfully thick. You know what they say, I like them slick, hard, and creamy. I should not have said that on camera. Okay. Oh no, I'm gonna get canceled. Let's call this right here, and actually this is a little too bright. I'm gonna blend in with the white, so choose dark green and dark blue. So, we can call this height from here all the way up there 8 for the height of the equilateral triangle. We can call this fellow right here, the distance from the bottom, BC, to that axis that we have here, we can call that y. Now, here's the thing. This takes a lot of intuition and skill to think of. So, what you need to do here is you need to use a fancy little something called torque bound. Since it was a mass m in the center, all three of the bodies experienced equal torque. All three of the legs experienced equal torque. they experience a torque that was mg times some random length, which I believe is the apothem, divided by 3. So, some length L over 3. So, that basically tells us the most weight it can handle is mg over 3 for each leg. That means that, no, never mind. We're not going to do that demonstration right now. So now we have to do a little something called torque balance. So, what does this mean? Well, this triangle, we don't want it to rotate or break. So, that means that it has to be in equilibrium. And there are 2 conditions for equilibrium. 1, net force equals 0. And 2, net torque equals 0. And now, the second one is the more important one to us. Why? Well, because what we can do is, since we have an axis here, we consider BC as just one entire side. So, what is the torque that this mass, the weight of this mass exerts on BC? Well, it's going to be F, which is 2/3 mg, times R, which is y. You might ask, where's the sine theta in FR sine theta? Well, think about it. We have this axis, and since we're looking at a bird's eye view, this is going into the page. In other words, if you turned it, then we would be looking at something like this, which means that the 2 axes we're looking at are perpendicular. The weight and our axis are perpendicular, and sine 90 is 1. So, that's that. And the same can be said about the normal force, except that the normal force is going to point this way instead. Alright, so, 2/3 mgy, right? And now, what about the torque here? Well, it would be 2/3, well, no. How can we express the torque here? Well, instead of using 2/3 mg, 2/3 mg is going to be the total normal force by the entire table. But for BC, we can just express it as FB plus FC. That's our force. And then our radius is y, and our torque is torque BC. What about our torque A? Well, our radius is h minus y, which is this length right here. H minus y, and FA. And keep in mind that Fn is 2/3 mg, because it has to hold up the mass. And Fn is also the same as Fa plus Fb plus Fc, because all of these 3 are the individual forces of the table legs holding everything up. So all of those together must sum up to the table's total force. Alright, so now let's talk about this torque. So the key thing here is these torques have to be equal. Why? Well, let's imagine what happened if this thing started rotating. So this is B, this is C, this is A. We can think of it as rotating around this axis that we have right here. So if it rotated like that, then B would rotate this way, but A would rotate this way if A broke. And B would rotate this way if the leg B broke. So this is counterclockwise. Well, this right here is clockwise. So, is that right? Yeah. So that means that A and B are opposing. So torque A is just going to be equal to minus torque BC, or vice versa. But it's the exact same thing. So, how can we say that in other terms? Torque A not equal to minus torque BC. We could say torque A minus torque BC is equal to 0. So torque A has to be equal to torque BC. Why do we put a minus sign? Well, because BC is going in the opposite direction. If we define CCW to be negative, we can define CW to be positive, thus this is positive and this is negative. We can do the same thing, but vice versa, if we define CCW to be positive and CW to be negative. That was a little bit of blah, 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 blah. But anyway, we have this equation now. tau A equals tau BC. So, tau A, we said, was h minus y FA. And tau BC, what was that? Y of FB plus FC. Now that gives us FA8 minus FAY equals y times FB plus FC. And now when we bring this to the other side, it should be obvious what we have to factor. We get FA8 equals y, FA plus FB plus FC. But what's FA plus FB plus FC? As we said before, it's 2/3 mz. So that means that FA8 is equal to 2/3 mgy. Now, what can we say? Well, we can say that, I'm kind of bugging over here. But, oh yeah, the max weight that any leg can take is 1/3 mg, which we discussed over here. Which means that the max force leg A can apply is mg/3. Which means that we can just plug in that max force over here to obtain the max height, h, or the maximum value of y. So if we plug in 1/3 mg, h equals 2/3 mgy, it should be obvious that h has to be equal to 2y, or y must be h/2. And that's the maximum, because if we make FA smaller, let's say 1/6 mgh, then what do we get? Well, we get h equals 4y, which means y is even smaller, h/4. So h/2 is the maximum y. And if y is any bigger than h/2, snap, leg A must break. So now, that means that half of h right here is the golden rule. Let's put this, yeah, it's alright. That is the golden rule. But by rotational symmetry, remember when I said you can make the axis parallel to any one of those sides earlier? Well now, let's rotate this. And for you to better see what I'm talking about, I'm going to redraw everything here. Our golden rule is right here, but now let's rotate this. The same thing applies to a shape that looks like this, because it's the exact same equilateral triangle. So that means max y is still 1/2 h. So that's the second defining line. Once you rotate it 120 degrees again, it's still also an equilateral triangle, and y must be equal to 1/2 h. So that means this length must finally also be the max h. And these three defining lines give us the final area that is the correct answer. So, an equilateral triangle that looks something like this is the correct answer, which I believe would be choice A. Thank you everyone for watching. This was probably the hardest one